So this is actually the continuation of the previous session. So in previous session, I have mentioned these contents that are in week 1. So today we will try to discuss about how to find roots, how to find powers of a complex number. Then you will see some problems which defines with inequalities or equalities. So in that case, how can we find the set of points, or how can we describe the regions? So that is the important one. Let's start from the very beginning. This is the continuation of previous consultation session. So here we will mainly learn how to find roots, how to find roots of an equation where complex number is involved. Then how to compute powers. That means powers of a complex number. And then we will try to see how to find principal argument. So principal argument is denoted by ARG of Z. That means here you can see that capital letter A. That is the difference between a small a RG of Z. So this is called the argument theta, and this one is called the principal argument. So after this, we will try to focus on how to compute the powers of I. And then we will try to describe any region. So these are the contents that we are going to look today. So first of all, let's talk about the formulas or forms that we have in complex analysis. So you know about Euler's identity. It is also known as Euler's formula. So what is Euler's formula? It is e to the power I theta, that is equal to cosine theta plus I sine theta. So this is called Euler's identity. We have to know what is the Moivre's theorem. So the Moivre's theorem is mainly cosine theta plus I sine theta power. Let's say we have n. So cosine theta plus I sine theta to the n. So at that time, what we have to do? The formula or theorem says that it will be cosine n theta plus I sine n theta. So this is called the de Moivre's theorem. So we can make a relation in between Euler's identity and de Moivre's theorem. You can see that cosine theta plus I sine theta can be written as e to the power I theta. It is true for all cases, but remember, this n should be integer. We can make a relation between Euler's identity and de Moivre's theorem. So that will be easier for us to compute the powers and also find the roots of any equation. So cosine theta plus I sine theta, that is known as e to the power I theta. So with power n. So now we can write it is e to the power I n theta. So that is, you can think about this n theta as a single theta. So cosine theta plus I sine theta, that is e to the power I theta. So this is the relation between Euler's identity and de Moivre's theorem. That means where you have theta, input n theta. So this is the advantage of using de Moivre's theorem in complex analysis. The relationship between Euler's identity and de Moivre's theorem is very important. So besides this form, I would like to write another form of Euler's identity. Suppose we have e to the power negative I theta. So in that case, what we can do, we can just make a simplified form, that is e to the power I negative theta. So it is also same as the previous one. Now we can apply the same technique, that is e to the power I theta, that is cosine theta plus I sine theta. Now you know that cosine negative theta, that can be written as cosine theta, but sine negative theta, that is negative sine theta, and we have also I. So we have already generated another form. So if we have e to the power I theta, that is equal to cosine theta plus I sine theta. Also, if we have e to the power negative I theta, we can directly write cosine theta negative I sine theta. We have actually two forms which are known as Euler identities. And the second form can be found by this way. So this is the simplification, how we can find the second form of Euler's identity. So besides Euler's identity and de Moivre's theorem, you need to know another concept, that is about argument theta, that is argument of z. If z equal to x plus yi is a complex number where x and y are coming from real number set, x is called the real part and y is called the imaginary part of z. Whenever we are trying to find the argument theta, so that is written as arg of z. Here be careful, I have written a small arg. So this theta can take a set of values. That means this set is infinite. We can take any values of argument. So you will understand if I give you the geometrical interpretation. Suppose we have a complex number in first quadrant. Let's say this is 60 degree from positive x-axis. This is also known as counterclockwise direction. That is, we are coming from this direction. So the angle that we have here, or the argument that we have, is equal to 60 degree. So whenever we are coming from the positive x-axis to this green colored line, we are getting this point. Let's say this is x comma y, which is the complex number. So the same point can be found if we make a rotation with 360 degree. So that means besides 60 degree, we can add 360 degree. Then we are getting the same line. So this will give us another result, and that is it is 420 degree. So by coming with one rotation, we have found another angle. So with that angle, we are getting the same line. So this will not affect the result. Okay, so that means the result will be same as before. We can make another rotation, that is, besides this angle we can add another 360 degree. So that means theta plus 2 n pi. This is the concept. If we make one rotation, let me use here k. So because in last consultation I have used k here, so that's why I'm using k here. So let's say k equal to 1, that means we are using one rotation. If k equal to 2, we are coming by 2 rotation. K equal to 3, so 2 times 3, 6, so 6 pi. So besides theta, we are adding 6 pi, and we are getting the same line. We are getting the same point, that is the complex number. So this is for counterclockwise direction. That means you can easily understand that the argument that we see here, argument of z, is not unique. It can take multiple values. It can take set of values. So we can go up to forever, and we will get the same point. So suppose we have the same point, and you know, complex number can be a point in complex plane that is known as z-plane, where x-axis is the real axis and y-axis the imaginary axis. So this time what we can do, suppose we have the angle theta as 60 degree, but now we want to come from clockwise direction, and our target is to get the same line. So instead of coming from counterclockwise direction, we want to come from clockwise direction. So here we are coming from clockwise direction, so we are getting the angle. So that angle can be found if we subtract 60 degree from 360 degree, that is negative 360 degree. So coming from counterclockwise direction or coming from clockwise direction doesn't affect our result. So we are getting the same line. Let's say we can make another rotation. We are getting the same line. We can come from another rotation. We are getting the same line. So that means the angle that you have, with that angle you can add negative 2k pi. So if k equal to 1, that is denoting the first rotation clockwise. If k equal to 2, second rotation clockwise. If k equal to 3, third rotation clockwise. So why not we generalize the concept? That is, previously we had theta plus 2k pi, and now we have found theta negative 2k pi. So now we can write that argument of z, that is equal to theta plus 2k pi, where k equals 0, plus 1 or minus 1, plus 2 or minus 2, plus 3 or minus 3, and this is the continuation. So that means k can be positive, k can be negative. If k is positive, it is denoting counterclockwise rotation. If k is negative, it is the clockwise rotation. So that means for clockwise rotation, we have this formula that can be thought like this way. That is, subtraction is one kind of addition. So 2 negative k pi. So that means k can be positive, k can be negative. So that's why we have written argument of z that is equal to theta plus 2k pi. Try to understand that the argument we always see that is not unique. It is not unique. It can take multiple values by adding 2 pi, 4 pi, 6 pi, or by adding negative 2 pi, negative 4 pi, negative 6 pi, and so on. So our first topic is how to find roots. So let's solve some problems, and then you will understand how we can find roots of any equation where complex number z is involved. So suppose we have z cube equals I. We want to solve this equation. So our target is solve the following equation. So here you can see that we have z cubed equals I. So depending on the highest power of z, we can easily understand that there will be 3 solutions. And in my last consultation, I have solved a similar problem like z cubed negative 1 plus I. So for this power 3, we actually have 3 solutions. So the solutions are denoted as z0, z1, z2. And if we try to find more solutions, that will be the repetition of the previous solutions. So that is the concept. So using that concept, we are trying to solve this problem here. So first of all, what we have to do, we need to keep only z in left side. So if we try to do this one on right side, we will have I to the 1 over 3. So this is the first step, what we have learned in our last session. So z cubed equals I. Our step 1 is keep z in left side, and on right side you will get I power 1 over 3. So now you can see that on right side, inside the parenthesis, we have a number that is a complex number. So let's denote that complex number as a new number. Let's say this is z1. So z1 equal to I. So z1 equal to I can be written like this way: 0 plus 1I. So from here, we can easily say that here x equals 0 and y equals 1. So our target is to convert this number that is in rectangular form to polar form. So in next step, we have to convert this one as to the polar form. So we know that if we have z equals x plus yi, that is the rectangular form of a complex number, that can be converted to z equals r e to the power I theta. So that is called the polar form. So using this concept, we can convert the rectangular form that is inside the parenthesis to the polar form. So now what we have to do, we need to find the modulus, because here r is present, and we also need to find the argument theta. So in this case, you have to find the argument based on the location and with the formula tan inverse y over x. So here the modulus r, it is root over x squared plus y squared. So let's try to compute. The value of x is 0, so 0 squared is 0, and y squared, that is 1 squared, so we have 1, so r equals 1. We have found the modulus r equals 1, and let's find theta. So it is tan inverse y over x. So what is the value of y? Y is 1 and x is 0. So that is 1 over 0, that is undefined infinity. So we know that tan inverse infinity is pi over 2. We have found argument theta. But besides using this formula, we need to locate this point. We need to identify where the point is located. So it is 0 plus 1 I. So that means it is 0, 1 point. So let's try to locate the complex number in Argand diagram in complex plane. So let's say this is 1, 0, 1. 0, 1 is located here. So that means this is the location 0, 1. So we can make an assumption, that is, what is the angle? It seems like it is 90 degree. And by our calculation process, we have found pi over 2. That is also 90 degree. So that means we are done. Whatever angle we have found, that is same as our assumption. Now we have found argument theta and modulus. So from this step, we can write z equals e power I theta over 1 over 3. So r is 1 or modulus is 1. Then I theta is pi by 2. And we have the exponent or power as 1 over 3. So let's simplify. 1 times this quantity is e to the power I pi over 2 with power 1 over 3. So this is z equals, but now we are in step 3. We need to apply the Movers theorem. So whenever I have started the session, I mentioned the Movers theorem. That is, if we have cosine theta plus I sine theta power n, then we can write cosine n theta plus I sine n theta. Or the simplified form can be the relation between Euler's identity and the Movers theorem. That is, we can also use this one, e power I theta power n, that is e power I n theta. So this is the same thing. But besides Euler's identity and de Moivre's theorem, we have learned that argument of z can be a set of values, that is theta plus 2k pi. So where we have the argument, let's input theta plus 2k pi. That is step 3. So we have z equals e to the power I, the argument theta, as pi over 2. So where we have pi over 2, let's input pi over 2 plus 2k pi. This is the concept that is coming from clockwise or counterclockwise. That depends on the value of k. But the point is, any argument of z can be the argument plus 2k pi. So where we have the argument, let's input that argument plus 2k pi. So here, if we do the same thing, then it will be e power I pi over 2 plus 2k pi. And besides this, we have power 1 over 3. So You need to understand that we are using the general concept of argument. Whenever we have applied this, we can mention that instead of z, we can mention zk, where k can be 0, positive, negative 1, positive, negative 2, up to infinity. So zk equals e power I. Now we can do the LCM, that is, it is pi plus 4k pi. We can focus on this identity. We know that e power m power n, that can be written as e power mn. So using that identity, we write e power I pi plus 4k pi over 2 times 1 over 3. That means that power is now multiplied. So we are using the concept e power m power n, that is e power mn. Now we can write zk equals e power I times pi plus 4k pi, and in denominator we have 2 times 3, that is 6. So finally we are done. We have found all the solutions, that is zk. Now we need to input k equals 0, k equals 1, k equals 2, like this. So now we have to check how many solutions we will have. So there will be 3 solutions. So we can start from always 0, that is k equal to 0, k equals 1, k equals 2. You can also start from k equals 1, then k equals 2, then k equals 3. So that is up to you. But my suggestion will be always, please start from k equals 0. We can also take k equals 0, k equals negative 1, k equals negative 2. But this is the simple form that we can use. Zk equals e power I pi plus 4k pi over 6. So here, now k is our input. We know that our equation is z cube equals I, and there will be 3 solutions. So let's start from k equals 0. Whenever we are inputting k equals 0, we are getting z0. So e power I pi plus 4 times 0 times pi, we will get just 0 here over 6. So that means we can do some simple calculations. So it is z0 equals e power I pi over 6. So now we have found a complex number. We know that there are 2 forms of complex number, that is rectangular form and the polar form. So rectangular form is z equals x plus yi, and the polar form is z equals r e to the power I theta. So the form that we have found here, that is in polar form, not in rectangular, that is in polar form, e to the power I theta, that is pi over 6. So what is the value of r? We have already found that r is 1. So that means every time the radius is invisibly 1. So we have the radius as 1. We have the modulus as 1. So why I'm coming with the notation radius? The term radius is used because the solutions lie in a circle. You will understand the geometrical concept within some moment. So for now, you can understand that the result that we have found is in polar form. We can also convert this to rectangular form in x plus yi form. How? By using Euler's identity. We know that e power I theta, that is cosine theta, plus I sine theta. So using this concept, we can write cosine pi over 6 plus I sine pi over 6. That means this is our angle, this is our argument. So cosine argument plus I sine argument. So you know that pi over 6, that is equal to 30 degree. So cosine 30 degree, that will give you root over 3 over 2, and sine 30 degree will give you 1 by 2. So we have found z naught equal to root over 3 by 2 plus 1 by 2i. This is our first solution. Similarly, we can find the second and third solution if we input k equal to 1 and k equal to 2. So let's input k equal to 1. So if we input k equals 1, then we are getting z1 e power I pi plus 4 pi over 6. Now e power I 5 pi over 6. So this is our second solution. Similarly, for k equals 2, z2 equals e power I pi plus 4 times 2 times pi over 6. So that is e power I pi plus 8 pi over 6. That means we are getting e power I 9 pi over 6. So this is z2. So here z1 and z2, both these are in polar form. So we can convert this to rectangular forms also. Let us do that. E power I theta, that is equal to cosine theta plus I sine theta. This is by Euler's identity. So cosine theta plus I sine theta. Similarly here, cosine theta plus I sine theta. 5 pi over 6, that is equal to 150 degree. That means cosine 5 pi over 6, that is cosine 150 degree, is equal to negative root over 3 by 2 plus sine 150 degree is 1 by 2 with I. So this is z1. Here 9 pi over 6 is equal to 270 degree. So cosine 270 degree is 0. Sine 270 degree is negative 1. So we are getting just negative I. So this is z2. So we have found all the three solutions: z0, z1 and z2. So let me write again, because we need to understand what is the geometrical significance of all the solutions or roots. So the solutions that we have found: z0, z1 and z2. Z0 is root over 3 by 2 plus 1 by 2i. Z1 is found to be root over 3 by 2 plus 1 by 2i, and z2 equals negative I. So we know that any complex number is a point. So z0 can be a point root over 3 by 2 comma 1 by 2. z1 is also a point negative root over 3 by 2 comma 1 by 2. z2 is also a point 0 negative I, so it is 0 comma minus 1. Here root 3 by 2 is approximately 0.8 and 1 by 2 is 0.5. So we are also trying to find the decimal values so that we can easily locate the point in our Gantt diagram. Negative root over 3 by 2, that is negative 0.8, 1 by 2 is 0.5, and this is 0 negative 1. So now we need to understand what is the geometrical interpretation of roots. z0, z1, z2 are roots of the equation z cube equals I. So we want to locate all the roots in our Gantt diagram. So let us locate the first point, z0. Let's say this is 1, this is 1, this is -1, this is -1. So the first point z0 is 0.8, 0.5. If it is 0.8 and it is 0.5, then our first point z0 is here. Similarly, z1, negative 0.8. Negative 0.8 will be here, positive 0.5 is here. So the second point is here. This is z1. z2, 0, -1. 0, -1. So the third point is here. So we can understand that the distance from origin to z0 or to z1 or to z2 all are same, because have a look here, if we compare with z equal to r e to the power I theta, so r e power I theta, so r is 1 for z0. Similarly, for z1, r e power I theta, so that means here r is 1. Similarly, for z2, r e power I theta, if we compare with this, 1 e to the power I theta, so r is 1. So that means you can easily understand that all the modulus are same. So 1, 1, 1. So this time modulus is acting like radius, because we can think about a circle with center 0, 0 and radius 1. So that means we can leave a comment that all roots of any equation where complex number is involved lie on a circle which is centered at the origin 0, 0. And this is true for all cases. So this is the geometrical interpretation of roots. That means any roots lie on the circumference of a circle. This is the circumference of the circle. So this is z0, z1 and z2. All these three solutions lie on this circle, which is with center 0, 0 and radius 1. So this time, since this modulus and this modulus are same, so we can think about a circle. So the modulus is acting like radius. So I hope you have understood this problem. So let's try to solve another similar problem, which is z to the power 4 equals 1 plus I. We can easily understand that this time we will have 4 solutions. There will be 4 roots, z0, z1, z2, z3. That means if we start from k equals 0, then k equals 1, k equals 2, k equals 3, we will get the 4 solutions. So first of all, what we have to do, we need to keep z on left side. On right side, we will get 1 over 4. That means z equals 1 plus I power 1 over 4. So here, on the right side, we have a complex number that is inside the parenthesis. So let us consider that number as z1. Let me write w1. Otherwise, it will be a confusion with this z1. And for the previous problem, I'm thinking that this is w1. So here, let's consider the complex number 1 plus I. So we need to convert this complex number that is in rectangular form to polar form, r e power I theta. So here we have also 1 over 4 at the power. So now our target is to find the modulus and the argument first. So the complex number is 1 plus I. Here x equals 1 and y equals 1. X part, y part. So the modulus r will be root over x squared plus y squared, that is root over 1 squared plus 1 squared, root over 2. So this is the modulus. The argument theta goes with the formula tan inverse y over x. So tan inverse y is 1 and x is 1. So tan inverse 1. So that means tan inverse 1 is 45 degree. That is pi over 4. So this is our argument theta. This is the argument theta. So now we need to locate, we need to be confirmed whether this is the correct one or not. So depending on the location of the point is 1, 1. So let's draw in Argand diagram. It is 1, it is 1. So the point is here, 1, 1. So we can easily understand that the argument lies in between 0 to 90 degree. That is, it is now 45 degree. So our assumption and this result is okay. So now from this part we can write z equals r e power I theta with power 1 over 4. So the value of r is root over 2 e power I theta is pi over 4 with power 1 over 4. So this is z. So now we have to do theta equals theta plus 2k pi, where we have theta. So that means z equals root over 2 e power I. This is our argument. So pi over 4 plus 2k pi. And whenever we are using this concept, at that time, instead of z, let's write zk. This time we can apply this identity a b power m, a power m, b power m, using ab power m, that can be written as a power m, b power m. So now we can write zk equals root over 2 power 1 over 4 with e power I pi over 4 plus 2k pi with power 1 over 4. So this is done. Now we need to do some calculations. So here, just like the previous problem, let's do the LCM. So LCM of these two terms is 4. So it is pi and it will be 8k pi. So it is 1 over 4. Now we can apply the identity, that is e power m power n, that is e power mn. So using this identity, we can write zk equals root over 2 power 1 over 4 e power I pi plus 8k pi over 4 times that power will be multiplied. So here 1 over 4 is in the exponent, is in the power, and now that power is being multiplied with the previous part, that is by using this concept. So here we have root over 2 power 1 over 4 e power I. In denominator we have 4 times 4, that is 16. So pi plus 8k pi, that is in the numerator. So finally we are done we have found all the solutions. So here we have generated one relation for k. So where k is 0, positive negative 1, positive negative 2, like that. But for this specific problem, we have actually 4 solutions because it is with z power 4. So that means we can start from k equals 0, k equals 1, k equals 2, k equals 3. So this is how we can find all the solutions. So this is done. So for k equals 0, we have z0, that is root over 2 power 1 over 4 e power I pi plus 0 over 16. So actually we are getting pi over 16. So this is our first solution. K equals 1, then we will get z1, so root over 2 power 1 over 4 e power I, we will get pi plus 8 times 1 times pi, that means 8 pi. So actually we have 9 pi over 16. So this is our second solution. Similarly, we can find k2, and for k equals 3, we can find z2 and z3. So this is how we can solve any problem where we need to find roots. So the first content that we need to discuss is done. We have learned how to find roots. So you will see that the concept that you have learned, that will be helpful in computing powers of any complex number. So let's try to discuss our second topic, how to compute powers. So powers of a complex number. Suppose we want to find the power of root over 3 over 2 plus 1 over 2i, and the power is 3. So we need to compute this power. So whatever concept you have applied in finding roots, same concept can be applied. So let me do this one. So first of all, again, whatever number we have inside the parenthesis, that should be converted to polar form because it is in rectangular form, x plus yi. So here, x equals root over 3 over 2 and y equals 1 over 2. So root over 3 over 2 has the numerical value as 0.8 and 1 over 2 is 0.5. Why we need these decimal values? Because it will be easier for us to locate the point correctly. So here, let us locate the point on Argand diagram or complex plane. It is 1, it is 1. So obviously it will be 0.8 and this will be 0.5. So the point root over 3 by 2, comma 1 by 2 is here. So any complex number is a point that can be directed from origin to the point. So it is acting like a vector. So now we can think about what will be the argument. The argument should be in between 0 degree and 90 degree because our point is in the first quadrant. So let us make an assumption for the argument, that is, it is in between 0 degree to 90 degree. So the complex number is root over 3 over 2 plus 1 over 2i. We need to convert this complex number to polar form. Root over 3 over 2 plus 1 over 2i with power 3. That should be converted to polar form r e to the power I theta. So let's find r. So r equals root over x squared plus y squared. So that means x is root over 3 over 2 and y is 1 over 2. So finally we have 3 over 4 plus 1 over 4. That means we are getting 4 over 4. We have the modulus r equals 1. What about the argument? We know argument theta, that is equal to tan inverse y over x. So tan inverse y is 1 over 2 and x is root over 3 over 2. So finally, the simplified form will be tan inverse 1 over root 3. So tan inverse 1 over root 3, that is equal to 30 degree. So the angle that is found from this calculation is 30 degree, and let's figure out with this assumption that we have made. Yeah, the angle is in between 0 degree and 90 degree, so it is okay. So we need to convert the degree form to radian form, so it is pi over 6. So r is 1, e power I theta is pi over 6 power 3. 1 times e power I pi over 6 is the same one, e power I pi over 6 with power 3. And now you know that if we have e power m power n, then we can write e power m n. So this is very easy. So e power I pi over 6 times 3. So it is done. Now we can do some simple calculations. That is, it is pi over 2. So now it is done. We have found the power of this number, and the power is 3. But if we target for the rectangular form, we can also find the rectangular form if we wish.
We will not be getting 3 answer of it.
No, this time we are finding powers. So what is the power of this? That means we are not solving equation. What will be the expansion of this part? This is our target. So be careful about the powers and roots. The steps are same. This is the difference between roots and power. So now we have learned how to compute powers. So our next topic is how to find principal argument. So remember, principal argument is denoted by ARG, where A is the capital letter. So ARG of Z. So principal argument always lies in between negative pi to pi. It can also be equal to positive pi. In other words, we can say principal argument is in between negative 180 degree to positive 180 degree, and it is denoted by capital A R G of Z. It can also be equal to 180 degree. So this is the main definition for principal argument, and principal argument is always unique. So this is the thing, that is negative pi to positive pi, and it can be equal to pi, and it is denoted by capital letter A R G. There is a difference between argument and principal argument. Argument is denoted as small a R G of Z, and principal argument is capital A R G of Z. So this can take a set of values. You have learned that it is theta plus 2k pi, so multiple values are coming here, but here we will get only unique value, we will get only one value. So let's try to find. Suppose the question is find the principal argument of Z equals a negative root over 3 negative I. So let's try to find this time principal argument. So principal argument actually comes from this argument. Since this argument actually takes a lot of values, so out of all these values, one value that is known as principal argument. We have z equals negative root over 3, negative I. This can be thought to be a point, that is negative root over 3, negative 1. So let's try to locate this one in Argand diagram. It is actually negative 1.73, comma, negative 1. This is the numerical value of this complex number. So let's try to locate the point. It is actually in which quadrant we have to find out. So it is negative 1, negative 2, negative 1. So negative 1.7, negative 1.7 will be here, and then negative 1. So now this is our point that is known as root over 3, comma, negative 1. So any complex number is directed from origin, and we know that the first angle or argument that we understand, it is from positive x-axis to the line. This argument is normally from positive x-axis to the line that we have drawn. So here, first of all, we can make an assumption that the angle that we have from positive x-axis to the line is actually in between 180 degree to 270 degree. So this argument is small a rg. This is in between 180 degree and 270 degree. This is our first assumption. So let's try to find the argument first. So we know that small a rg of z, it is equal to tan inverse y over x. So let's plug the value of y and x. So our y is negative 1 and x is negative root over 3. So negative 1, negative root over 3. So by simplifying the previous part, we are getting positive 1 over root 3. So tan inverse 1 over root 3, that is actually 30 degree. So this is 30 degree. So we have found argument of z. Be careful about the symbol. It is a small letter a. So it is 30 degree. So now we have to point out the location. So our location says that the argument, it should be in between 180 degree to 270 degree. That is in third quadrant. So what we have to do, you can check my previous consultation. So where I have mentioned that if a complex number is in third quadrant, then what we have to do? If we have a complex number in third quadrant, then we have to add 180 degree. For this case, the angle or argument that we have found 30 degree, it is actually found by this way. If we extend the main line in backward portion, we will get the 30 degree argument. So now to have the total argument, what we have to do, you can see that this angle seems to be 180 degree. With this, we have to add 30 degree. So the correction is 30 degree plus 180 degree. That means 210 degree. This is our argument of z. Now it is going with our assumption, that is, depending on the location, our argument lies in between 180 degree to 270 degree. So we know that this argument can be a set of values. We can write this one as 210 degree plus pi plus 4 pi plus 6 pi. We can subtract negative 2 pi, negative 4 pi. So we can go on. Like this way, we'll find so many arguments. But we need to find out of these all arguments, which one is the principal argument. This is our point, and this is the angle. So can it be the principal argument? Yes or no?
No, sir.
Principal argument always lies in between negative 180 degree to positive 180 degree, and it can be also equal to 180 degree. Now, coming from the concept of rotation counterclockwise or clockwise, let's say we are using counterclockwise. If we make one full rotation, that means we are coming 2 pi with the previous angle. If we add 360 degree, we are getting the same line. So that doesn't affect our result. So we have 570 degree. We can also come with the second rotation. Then we have to add another 360 degree. So this is also another argument, which is known as small a. So a, r, g, opposite. So it can be the argument. This one can be the argument. But whenever we are coming from counterclockwise direction, we are getting larger and larger values of argument. So why not we come from clockwise direction? So again, the point is here. It is 210 degree. So now we want to come from clockwise direction, because our target is to find the principal argument. It doesn't matter whether we come from clockwise or counterclockwise, but what case we have here, whenever we are coming from counterclockwise direction, the arguments are getting larger, but we should find one angle that is in between negative 180 degree to positive 180 degree. So that's why our counterclockwise process is not working. Now let's come from clockwise direction. From here to here, the total angle is 360 degree. So now we are looking for this one. So we have the main argument as 210 degree previously. Now to have this result, we are adding negative 360 degree, and this is becoming negative 150 degree. So it is also our argument, but let us check with our principal argument concept. So principal argument lies in between negative 180 degree to positive 180 degree. It can also be 180 degree, but this is unique. Only one value we will find out of all the arguments. So now tell me, is it the principal argument?
Yes, sir.
Yeah, principal argument. So we have found our principal argument. So this is one unique value. If you have any doubt, you can also add another clockwise rotation. So we are going with another clockwise rotation. So that means the angle that we have found now, with this angle, let us add again negative 360 degree. So negative 150, negative 360. So it is equal to negative 510 degree, and we are getting the same line. So it doesn't affect our result. But the main thing is, it is argument. It is also argument. This is also another argument. This is also argument. But out of all these arguments, only we have one unique result, that is negative 150 degree. So it is the principal argument, because it is going with this inequality. So this is going with the definition of principal argument, and you know the definition that principal argument lies in between negative 180 degree to positive 180 degree, or it can be equal to 180 degree. But the main theme is principal argument is unique. I hope you have understood how to find principal argument. So let's now focus on the powers of I. So now we are trying to find the powers of I. Just a small letter I that is known as imaginary unit. So suppose we know that I equals square root of -1, so it is already known to you. If we write I squared, then the value will be -1, because I is square root of -1. So I squared can be found by multiplying I and I. So that is root over -1 times root over -1. We are getting -1. So this is I squared. If we try to find I cubed, so I cubed equals, we can say I squared times I. So already you have found I squared as -1, and let us keep I. So -1 times I is -I. So this is I cubed. This is I squared. And let's say this is just simple I. Similarly, what will be the case for I to the power 4? We can think about I squared times I squared. So -1 times -1. So -1 times -1 is +1. So I to the power 4 is 1. So we now know that I squared is -1, I cubed equal to I to the power 4 equal to 1. So what will be the case if we look for I power 100? If we look for I power 99? If we look for I power 202? So at that time, what we can do? We can maintain a sequence. Suppose we are looking for I with any power, and the power is an integer number. So try to divide that power by 4, and then you will get the remainder here. So I to the power something, that will be I power remainder, and you will see that the remainder will lie in between 0, 1, 2, 3 and 4. So suppose you have I power 0. Always I power 0 is 1. Anything power 0 is 1. If you have I power 1, that is I. If you have I power 2, that is -1. If you have I power 3, that is negative I to the power 4, that is 1. But what will be the case for I with higher powers? So that is our target for now. Let's say we are trying to find I 100. So what we have to do, let us divide 100 by 4. So that means if we divide 100 by 4, we will get, let's say 2, that means 8, we are getting 20, and now, so the remainder that we have found is 0. So I have mentioned that I to the power anything, that is equal to I power the remainder. So what is our remainder at this moment? It is 0. So it is I power 0. So that means I power 100 is equal to I power 0. And you know what is I power 0. So I power 0 is 1. Similarly, let's do another calculation. Suppose we have I power 202. We want to figure out the value for I power 202. So again, the power that you have, that should be divided by 4. So let us do the calculation. 50 times 4 is 200, and we have the remainder 2. So this is the remainder. So that means I power 202, that is I squared. So you know what is I squared. I squared is -1. So this is how we can find the powers of I if the powers is an integer. Suppose we need to evaluate. We have I to the power 100 plus I power 5, I power 21 negative I power 7. So we are trying to simplify this form. So in every terms, both in numerator and in denominator, we have powers of I. So how to do the simplification? The process is always same. We have to divide the power by 4 always, and you will get the remainder. Sometimes remainder may be 0, 1, 2, 3, 4. So I power something that is equal to I power remainder. So here, let's do the first calculation, I power 100. So 100 is divided by 4. So we will get the direct solution, that is 25 times 4 is 100. So we get the remainder as 0. So I power 100 is equal to I power 0. Now come to the part I power 5. So let's divide the power 5 with 4. So 1 times 4 is 4. We are getting the remainder 1. So that means I power 5 is equal to I power 1. Let's come to the point, what will be I power 21? So 21 is divided by 4. So we are getting 21 by 4, that is equal to, it will be 5 here. 5 times 4, that is 20. So 1. So this time the remainder is again 1. So I power 1. Negative I power 7. So 7 divided by 4. 1 times 4 is 4. So we are getting 3. So the remainder is 3. That means I power 7 is equal to I power 3. So now, whatever simplified form we have, we know the value for all these things. So I power 0 is 1. I power 1 is I. In denominator, I power 1 is I. And I power 3, you have seen that I power 3 is negative I. So this is negative I. So we can write 1 plus I plus I, that is 1 plus I over 2I. So this is our simplified form. So we can keep our answer here, but the concept is, don't forget the standard form of complex number. We know that standard form of complex number is z equal to x plus yi. So here we can write z equal to x plus yi. So using this pattern, we can rewrite this. You are going to evaluate this one, and there is a concept that is attached. Write your answer in standard form. So we have to write in standard form. So how can we do this? We can do this one by finding the complex conjugate of the denominator. So in denominator, we have 2i. So its complex conjugate will be negative 2i. So that means we have to multiply both numerator and denominator by the conjugate of the denominator. So if we do this calculation, you can see we are getting the previous equation. Now we can do the simplification. Negative 2 times 2, that is negative 4, I times I squared. And here, let us multiply this number with negative 2i. We are getting negative 2i, negative 2i squared. So we have finally negative 4 in denominator, and you know that I squared is negative 1. So I have written the value of I squared. In upper part, we have negative 2i, negative 2. Again, I squared is present, so negative 1. So finally, this is 4, negative 2i plus 2. So we can write by this way, 2 negative 2i by 4. Still, it is not in standard form. Just to have the standard form, confirm about this one. That is z equal to x plus yi. So what we have to do now? We can just separate the terms. 2 by 4, positive negative 2i by 4. So it is now 1 by 2, positive negative 1 by 2i. So this is now x plus yi. So it is now in standard form. So sometimes you may be asked to evaluate and write your answer in standard form. So if you have to find the standard form, then after this part, you have to find the complex conjugate of the denominator and multiply that in both numerator and denominator and do some algebraic calculation. So this is how we can deal with the power of I if the power of I is an integer. So this part is also done. Now let's come to the main concept that we have, how to describe any region. Here you will see some inequalities describing set of points that are in complex plane. Or in other words, sometimes you may see describe the locus. So we have to know how to describe the locus. So describing the locus. So what does locus means? It is the set of points. Same thing. Before starting this one, we have to know some concepts. So first of all, we need to know what is disk. So let me write directly that suppose you have modulus of z negative z naught less than rho. Modulus of z negative z naught less than rho or less than equal to rho. It depends sometimes. So this is called disk because it will give us a circular graph. So that's why it is called disk, because it is looking like a disk. I'm writing rho here because already R is known as the modulus. So just to have another notation, I'm writing rho so that you do not get confused with rho and R. So rho is a separate thing, that is the radius. Please try to note down that disk is denoted by modulus of z negative z naught less than rho or less than equal to rho. We also need to know what is annulus. So annulus is something where we have the same quantity, that is modulus of z negative z naught with rho. But this time we have another value. But the point is we have rho 1 to rho 2. So rho 1 less than modulus of z negative z naught less than rho 2. So this is called annulus. So what does it mean? Disk is just a circle, but annulus is denoting two circles. So first one with radius rho 1 and the second one with radius rho 2. So this is called disk and annulus. And these things are very important whenever you will start Taylor and Lorentz series. So that's why you need to know. So let me start with a problem so that you can directly understand what I mean to say. So besides describing set of points or describing the locus, the alternate form will be describing the region. Suppose you have one inequality. Modulus of z negative 4 plus 3i less than 5. So you can think about this one. Modulus of z negative z naught. We have modulus of z negative z naught is 4 negative 3i. So this is going with this concept. So it will finally give us a disk. So for now, for simplicity, let us work with equal sign. So suppose we have equal here. Now we need to describe what does it mean. So the question is, describe the set of points from the following. So the expression or equation that we have, modulus of z negative 4 plus 3i equals 5. And just to have the notation with disk, we are writing this number in a group. So we have written the number in parentheses so that it goes directly with this concept, and it is rho. So I have mentioned that it can be less than, it can be equal. If you have less than, so you will get a different graph. If you have equal sign, you will get a different graph. If you have greater than, you will get a different graph. So it depends. So let me solve this one. For solving this, we need to go step by step. In step 1, we need to input x plus yi where we have z. Then in step 2, suppose you have modulus of x plus yi. So we know that it can be written as square root of x squared plus y squared. So in other sense, we can say that real part is squared plus imaginary part is squared. So this is the thing what we have to do in step 2. Then in step 3, we have to do some algebraic calculations so that we reach to an algebraic equation having x, y. So there will be no z anymore. There will be no z anymore. We want to describe the set of points. Set of points means we need to draw the graph for this equation. So in step 3, we have to do some algebraic calculation. And in step 4, we have to draw the region. That means we have to draw the graph. So for now, we are inputting x plus yi where we have z. And this is always true for all cases. Where you have z, you can input the standard form. So x plus yi negative 4 negative 3i equal to 5. So now what we can do, we can just write in simplified form. So it is negative 4 plus 3i equal to 5. So here let us group the real parts and then imaginary parts. So here the real parts are x negative 4 and the imaginary parts are yi and 3i. So yi and 3i, on right side we have 5. So we can write in this way, x negative 4 plus y plus 3i. I is factored out because I is common in both expressions, yi and 3i. So that's why I is factored out. Now, this is real part and this is the imaginary part. So we want to skip this modulus sign. So whenever we need to skip the modulus sign, so at that time, we need to go with this concept. Square root of real part is squared plus imaginary part is squared. So let's try to understand. It will be square root of real part is squared plus imaginary part is squared equal to 5. So finally, what we can write, we can simplify. So we can square on both sides. We are getting x negative 4 squared plus y plus 3 squared equal to 5 squared. So this equation is known to us from the concept of geometry. We can also write by this way, that is x negative 4 squared plus y negative 3 squared equal to 5 squared. So this is actually denoting the equation of circle. Because we know that x negative a whole squared plus y negative k whole squared equal to 5 squared, that is the radius squared. Let's say rho squared. So now we can easily understand that what is the value of a's and k. So a's comma k, that is the center. It is an equation of circle with center a is k and radius rho. So a is k is 4 and negative 3 and the value of rho is 5. If you are unfamiliar with rho, you can also write r, that is not a problem. So that means the expression that we have previously, it is actually denoting a circle. So we can draw the circle easily. 4 negative 3, 1 2 3 4, negative 1 negative 2 negative 3. This is the center. One, two, three, 4, 1 2 3. So this is our center and the radius is 5. You can draw by freehand. 1 2 3 4 5. 1 2 3 4 5. So we have found the circle. That means this is actually denoted by modulus of z negative 4 plus 3i equal to 5. So whenever we have this form, we can't understand what will be the graph. But by simplifying this one and reducing this to an algebraic equation, we can easily understand that this is just the circle. We can write this one or this one. That means the set of points is the circle. So now you have to know what is the function for equal, what is the function for greater than, what is the function for less than. Suppose we have the same problem. So we have understood that this is a circle with center and radius. Let's say we have the same expression like modulus of z negative 4 plus 3i less than 5. So it will be less than, 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 finally less than. So this is how we will reach to the conclusion. But how can we draw the graph whenever we have this sort of inequality? So we will get the same result, but since we have less than means the interior part. So it will give us this region, but not the boundary. If we have equal, then we have just the boundary. That means this is our result. We have to shade only the boundary or the circumference. If we have both less than and equal, then you will get the same graph, but this time for less than we have the interior part, and for equal to we have the boundary also. So the whole region is coming. In some textbook, the interior part, that means it is defined by this shaded region, and you can easily understand that the boundary is not included. So the boundary is drawn by the dotted curve. So sometimes you will see this. So if we have less than and equal, we will have both interior and boundary. Suppose we have the same expression, but we have greater than. All these things are important for Taylor and Lorentz series. You will see later on. So for now, you have to know how to do the calculations. So suppose we have greater than 5. So the circle is always the same, but if we need to describe what does it mean, since greater than is present, so it will be the exterior region. That means we have the outside boundary. We have the outside region. If we have greater than and equal to, so this time both exterior and for equal to we have the boundary also included. So that means from boundary to the exterior part is described by this set of inequalities. For equal boundary, that means the border is included. Just the greater than symbol, the border is not included. See, I didn't draw the straight line like this. I have maintained space here. So this is how we can describe the set of points. I have mentioned here disk and annulus. So let me do another problem. Let's say we have to describe 1 less than z negative 1 negative I less than 2. So again, the question is same, describe what does it mean, or describe the set of points, or describe the region, or describe the locus. The question may be in various notations, but the process of answering is same. We need to finally have the graph. What does it mean? Our target is to reach to x and y equations. So step 1, where we have z, let's input x plus yi, and the rest things are same. So I have already mentioned that whenever we have this expression, this inequality will just give us only one circle, and if we have this one, rho 1 less than modulus of z, negative z not less than rho 2, it will be 2 circles. So let us do the calculations quickly. So let's group the real part and imaginary part. These are the real parts. So x negative 1 is grouped plus yi negative I less than 2. So now 1 less than x negative 1 plus I is factored out. We have y negative 1 less than 2. So this is the time what we need to remove this modulus sign. So for that, we know square root of real part is squared plus imaginary part is squared. This is our real part and this is our imaginary part. So we can do by this way. 1 less than square root of real part squared plus imaginary part squared. See, I haven't written I here because it is not going with the concept. Only you have to keep real part squared plus imaginary part squared. So be careful. Now, just to remove this square root, we can square on all sides. So we have 1 less than x negative 1 squared plus y negative 1 squared less than 4. Actually, it's wise to write 2 squared and 1 squared form. So finally, we have reached to a conclusion. Now we have to understand what does it mean. So we can see 2 inequalities actually here, the first one and the second one. So let us subdivide. For 1, we can write like this: x negative 1 squared plus y negative 1 squared greater than 1 squared. 1 less than this. So this greater than 1 squared. Similarly, we have the second part: x negative 1 squared plus y negative 1 squared less than 2 squared. So we have 2 inequalities this time, but the main thing is we need to understand what does it mean. So it is actually going with x negative h whole squared plus y negative k whole squared equal to r squared or rho squared, like that. But this time we have greater than or less than, that doesn't matter, but it is actually giving us one circle for this one and another circle for the second one. So what is the center? Center is HK. So for both cases, the center is 1, 1. You can compare with HK and find that H is 1, K is also 1. So we have found our center, that is 1, 1 is here. So let us draw the first circle. So this circle is with center 1, 1 and radius 1. Radius 1. So radius 1, 1, 1, 1. We can easily draw the graph. So this is the first circle. It is done. We will try to think about the greater than and less than later. But for now, let us draw the graph. So for the second circle, we have radius 2 and center is same. center is 1, 1. So this is 1, 1, and radius 2. This is 1, this is 2. So 1, 2, 1, 2, 1, 2, 1, 2. So by this, we can easily draw. So we have the second circle. It is going with annulus, rho 1 less than something less than rho 2. So now the point is, what will be the region for the first case and the region for second case? So let's think about the first case. In first case, we have greater than 1. So this is 1. This circumference is 1 distance from the origin. So since we have greater than, so we have the exterior. Greater than means exterior, so we are going outward direction. We are going in outward direction. For the second case, we have less than. So less than 2. This circumference is for radius 2. So for less than, we have the interior region. So by combining these two things, we have the interior part, but not the boundaries. Suppose we have the same sort of inequality. So this time, instead of less than, suppose we have equal. So we will get the same graphs. This is our first circle, and this is our second circle. So for the previous case, we are shading the inside region. But since we have now equal on both sides, so both boundaries are attached. Suppose we just have equal in left side, but less than only in the other side. So that means for this case, the region will touch the first circle, but will not touch the second circle. So this is how we can think about. So that's all from me. I hope you have understood all the concepts that you have in week 1, and I have tried to discuss all the concepts within these 2 sessions. So have a good time. Thank you.